So before we get stuck into the combinatorics, just something about factorial notation, because it's used a lot in combinatorics. That's the actual definition of factorial. So 0 factorial is defined to be 1. But then after that, n factorial is simply n times n minus 1 factorial. So you know 0 factorial is 1, so then you can create 1 factorial, and then once you've got 1 factorial, you can create 2 factorial, and 3 factorial, 4 factorial. How far did I go? All right, and all the way down, and so n factorial would be n times n minus 1 factorial, which is n times n minus 1 times n minus 2 factorial, which is, and so on and so on and so on, and you'd keep going until you get down to 1, of course. So when we see something like 12 factorial over 9 factorial, it cancels because, of course, the 9 factorial is inside the 12 factorial. And so basically we roll it out. Now, I'm not saying you wrote all these lines in, by the way. So we roll it out and we say, well, 12 factorial would be the same as 12 times 11 factorial, and 11 factorial is the same as 11 times 10 factorial, and well, 10 factorial is the same as 10 times 9 factorial. Oh, now the 9 factorial is cancelled. So we end up with 12 times 11 times 10, 1,320. In reality, we'd just probably go straight to 12 times 11 times 10. 16 factorial and 10 factorial, 7 factorial. Well, it makes more sense to cancel the bigger factorial. So the 10 factorial would roll out, and I would be left with then on top 16 times 15 times 14 times 13 times 12 times 11, because we've cancelled the 10 factorial. And then on the bottom we have 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is where we get to have some fun and do some cancelling. 7 times 2 is 14. So that cancels. I've now got this. What can I do now? 5 3s are 15. That cancels. 6 4s are 20. Oh, damn. But I can go 6 and a 12 leaves 2. And then, of course, 2 goes into 4, and 2 also, oh yeah, we end up with 4 times 2. We get 4 times 13 times 2 times 11, which is 4 times 26 times 11, which is 104 times 11, which is 1,144. But, of course, we could have algebra. That's why it's still important to understand what cancelling happens here, because we can't go to our calculator with algebra. So I have 1 on k factorial plus 1 on k minus 2 factorial. We've got to get the common denominator. So in this case, it would be the higher factorial would be the common denominator. Because, and that explains it a bit more, because k factorial, of course, we could write as k times k minus 1 times k minus 2 factorial. So the first fraction would become 1. It stays the same, although I've written it at the end for some reason there. And the second fraction would have k times k minus 1 on top. And then we can play around with that. The top doesn't cancel, so I'll just leave it like that. K squared minus k plus 1 on k factorial. Let's now move into this idea of permutations, and we start with a very simple idea, that being the basic counting principle. You see, this whole topic of combinatorics is just about working out how many times something can happen. Do you remember in probability we said we're not actually that interested in what is inside the sample space. We're more interested in how many things there are, so we can work out probabilities. So this whole idea of combinatorics is that, working out how many things are in that sample space. So the basic idea is this. If one event can happen in m different ways, then after that another event can happen in n different ways, then the 2 events can occur in m times n different ways. So a very basic idea. 3 dice, we're going to roll them. How many ways can the 3 dice fall? So, okay, we could look at this and say it's going to be 6 times 6 times 6, because the first die, well, bang, we roll that, and yeah, it's got 6 different possibilities it could have. The second one, it would also have 6 different possibilities, and the third one would have 6 different possibilities as well. So we know there are 216 different possibilities, sort of different. Some of them would look the same, but aren't necessarily the same. That then brings up this idea. I didn't really have to go 6 times 6 times 6. If the number of ways of arranging n distinct objects with replacement in k different ways must be n to the power of k. So the 3 die, they all have 6 possibilities, so I could have just gone 6 cubed. In how many ways can all 3 dice show the same number? Well, that'll be 6 times 1 times 1. Because way of thinking about it is, yeah, sure, we might have rolled all three at once, but really it's no different to rolling one, then rolling another, then rolling another. So that first one, there's 6 different things it could have. But because I want all 3 to show the same thing, now the second one has only got one possibility. It's got to be the same thing. And the third one's only got one possibility. It's got to be the same thing. So we have 6 possibilities. That then brings up the logical probability question. Well, what's the probability that all 3 dice show the same number? Then we use our probability idea and say, well, that's 6 out of 216. Well, that simplifies down, 1 out of 36. Here's a really nice one from a very old HSC question now. Mice are placed in the center of a maze, and in this maze there are 5 exits. Each mouse is equally likely to leave the maze through any of those 5 exits. Thus, the probability of any given mouse leaving by a particular exit is 1 in 5. So 4 mice, and maybe we've just painted on their back some letters, because psychologists do that in experiments. They do things like that. So A, B, C, and D. And these mice behave independently. They're just running around. What's the probability that A, B, C, and D all come out the same exit? Okay. Total number of possibilities. Well, it's going to be 5 to the power of 4. 5 exits, 4 mice. So there must be 5 to the power of 4. 625 possibilities. So the ways that they go through the same door. The first mouse leaves, and they've got 5 doors they can go through. But now we want them all to go through the same door. So the second mouse would go through the same door. The third mouse will go through the same door. The fourth mouse. And so we'll end up with 5 possibilities there. So the probability, therefore, is 5 out of 625, which simplifies down to be 1 in 125. So the next thing they asked, what's the probability that A, B, and C come out the same exit, but D goes out a different exit? So A, B, and C use the same exit, D uses a different exit. This is how I thought about it. D, I'm going to say D leaves first. Again, the actual order they leave doesn't really matter. But D leaves first, so there's 5 choices. The next mouse is going to leave, but we don't want it to go through the same door as D, so they only have 4 doors. But now the other 2 has to go through the same door as that last mouse, and so they both have 1 way of leaving this maze. So there's 20 all up. Thus, the probability, 20 out of 625, which is 4 out of 125. So then they asked, well, what's the probability that any 3 of the 4 mice come out the same exit, and then the other one goes out a different exit? Well, we just worked out the probability that D uses a different exit. But everything's equally likely. So therefore, the probability that A uses a different exit must also be 4 in 125. The probability that B uses a different exit would be 4 on 125. The probability that C uses a different exit would be 4 on 125. So the probability that any of those mice use a different exit to the other 3, and the other 3 go through the same door, must be 4 times 4 on 125. 16 on 125. But there was another part. What is the probability that no more than 2 mice come out the same exit? So no more than 2 mice come out the same exit. Well, I'm going to use the complementary idea, because if you think about it, we've worked out the complement to that. Because if the complement to no more than 2 mice go out the same exit must be more than 2 mice come out the same exit. Well, we've just worked out 3 mice going out the same exit and 4 mice going out the same exit. So we've worked those things out already. So I'll go 1 minus the probability they all go through the same exit, minus 3 of them use the same exit, which we worked out, and so our answer is 108 on 125. So this brings us to the idea of permutations, a very specific type of arrangement. And so what a permutation is when the order that they come out of the maze, or whatever the arrangement is, that is important. So it is the actual arrangement of the objects we're interested in. So an ordered set of objects. So the first case, we've got n different objects. We're going to arrange them from a set of n objects. In other words, I'm going to use all the objects. I'm going to arrange them all. How's that going to work? We're going to arrange n different objects in a line. How many ways could we do it? So over in the corner over here, it's good to see you all looked, there are n different objects. Lovely, aren't they? Okay, we're going to get one of those objects and place it there. We're going to start our line. So the question is, how many ways? Well, there's n for me to choose from. So there's n different objects I could have put in that first place. Now I'm going to get the second one and put it in there. Now I've got n minus 1 objects to choose from. Then I'll get the next one, n minus 2, and so on, and so on, and so on. But because I'm using all of them, eventually I'll get to the point where there's just one object left. We'll say, right, just join the back of the line. Well, what have we got there? That's our n factorial. So it's simply n factorial. You want to arrange n objects, and the order is important, then there's n factorial ways of doing it. So we've got 5 boys, 4 girls. We're going to arrange them in the line. First of all, no restrictions at all. If there's no restrictions, then it's 9 factorial, because I don't care that there's 5 boys and 4 girls. I've basically got 9 people, or objects if you prefer. So there we go, 362,880. But what if it does matter? And we want to get this lovely pattern, and the boys and girls are going to alternate. The first decision we must make is, will we start with a boy or will we start with a girl? But in this situation, my choice is forced. I have to start with a boy, because otherwise I'm going to run out of people if I want to go boy, girl, boy, girl. So you always look after any restrictions first. So a restriction in this is, I must start with a boy. So there you go. There's only one way I can start, and that's the first one. It's going to be a boy. I've simply written down the number 1. I suppose I didn't have to write down the number 1. Okay, I haven't arranged anyone yet. Okay. Now I'm going to arrange the boys. Okay, righto. I know I'm going to start with a boy. You 5 guys, go and line up, will you? How many ways could that happen? 5 factorial. 5 objects are going to arrange themselves. So now I'm going to put the girls in. But there's now only one way they can be placed, because they have to be alternating. Now, within their own little group, there'll be 4 factorial ways they can arrange themselves, but then there's only one position they can be slotted in to make sure it alternates. So 2,880 ways of doing that. So therefore, the logical probability question to follow up with, what's the probability then that the boys and girls actually alternate? 2,880 over 362,880 simplifies down 1 in 126. And I'll tell you what, that's a heck of a lot easier than drawing a tree diagram. You imagine that tree diagram, it'd be huge, absolutely huge. But hang on a sec. They've said, no, we don't like this alternating thing. 2 of the girls said, no, they've rebelled. So we want to be together. Well, okay. Look after the restrictions first. So the first thing we have to do is to ensure that they're together. There will be 2 factorial ways. We go, all right, you 2 want to be together, work out which way round you want to go, will you? 2 objects, 2 factorial. Now, as far as we're concerned, those 2 girls are 1 object, because they're going to be together. So however one's placed automatically dictates how the other one's going to be placed. So they're now 1 object. So it means I've got 8 objects to arrange. A group of 2 girls plus the 7 other people. So 8 objects I've got to arrange, 8 factorial, 80,640. So that's if we use all the objects. But let's say we don't want to use all the objects. So we're going to order a set of k objects from a set of n, and k being less than n. In other words, I'm not going to use all of them, I'm only going to use some of the objects here. How does it change? Okay, we've got n objects over there in our corner, but we only want to arrange k of them. So how many ways can we do it? Well, it's going to start off the same. Got to get the first one, I've got n to choose from. And then I'll pick the next one, that's still the same. And then I'll pick the next one, that's still the same. But once we get the kth object, that's it, we're done. Well, the question is, how many ways would there be? It's going to be n minus k plus 1. Have a look at the pattern. When there was object number 2 was n minus 1. Object number 3 was n minus 2. So logically, object k would be n minus k plus 1. Ooh, that's a bit hard to work out. So we actually make this simpler by making it look more complicated. But what I've basically done is multiplied by the number of ways we could arrange all the objects over here that we didn't use. Right? So we said, hey, not going to use you. So we're dividing that out And so we end up with n factorial, the number of ways I could have arranged all the objects if I wanted to, but I'm going to divide it by the number of ways I could have arranged the objects that I didn't use. That's no longer important, so I divide it out. N factorial divided by n minus k factorial. But thanks to the wonders of modern technology, there's an even easier way of doing it. NPK, and there is a button on your calculator. Okay, I think it's either on the multiplication or the division. Looks like on my one it's on the multiplication button. But it's still important that you know where that came from, because again, if they're using algebra instead of numbers, you can't use your calculator to work it out. So, number of ways we can arrange all the objects divided by the number of ways we could arrange the objects that we didn't end up using. Letters of the word problems, but we're only going to create 5-letter words, and from our point of view, this is mathematics, not English. Any arrangement of 5 letters is a word. So, blems is a word, smelb is a word, robble is a word, and so on. How many different 5-letter words could we come up with? Well, it's going to be 8p5. 8p5. Because 8 is the number of letters we've got to use. I'm only going to use 5 of them. So the bigger number goes on top. 6,720 works out to be, if you didn't have your calculator handy with you, then it would be 8 factorial over 3 factorial, because there's 3 objects we're not using. So it'll be divided by 3 factorial. Now let's mix it up a bit. The word has to start with the letter P. Always look after your restrictions first. P, you've got to be in first place. Bang, there's only one way I can do it. I'll put it at the start of the word. 1, there it is. Now, I've got to get the other 4 letters, but it now becomes 7p4, because as far as we're concerned, the question now is, how many 4-letter words can we make from problems? And then we just add that to the P, and we've got our 5-letter word. So 7p4, 840. Well, okay, P's included, doesn't necessarily have to go in the first spot. But it can't go at the first part, we've decided. So P is included, but this time can't be in the first spot. And M, we don't like the letter M today, not going to use it. M is not going to be used. Look after the restrictions first. So I'm going to place the P, but this time there's only 4 spots I can put it in, because it's not allowed to go in the first place. So I've done that. Now I've got to place the other letters, but now it will be 6p4, because I'm not allowed to use M. So the question has now become, how many 4-letter words from robbles can we have? So 6p4, 4 times 6p4 gives me 1,440. 6 people are in a boat. It's got 8 seats, 4, spelt badly, on each side. What's the probability that Bill and Ted are on the left side and Greg's on the right? Probability, so I need to work out the total number of ways with no restrictions, because that will go in the denominator of our probability. That's the whole sample space. So it's 8p6, because there are 8 seats, we're going to use 6 of them, and a person sitting in a different seat would be a different arrangement. So yes, it is a permutation. So we've got 20,160 different ways we could sit in this boat. Let's now look after the restriction. Bill and Ted said, I will only go on the left side. So they now only have 4 seats. So 4p2, let's put them in the boat. Now for Greg, 4p1. 4p1 incidentally is the same as 4. So you could have just said, oh, well, there's 4 seats they could have sat in. And then we've got to arrange the other, how many people we got left? 3 still to go, haven't we? 3 still to go, and how many seats have we got left? 5. So 5p3. 5p3, they'll pick them. So we end up with 2,880. So now we can answer our probability question. 2,880 over 20,160, 1 in 7. There's a 1 in 7 chance of doing that. Another HSC question. Sophia, you've got 5 coloured blocks. Yeah, well done. 1 red, 1 blue, 1 green, 1 yellow, and 1 white. Ends up stacking them 2, 3, 4, or 5 blocks to form a tower. In other words, a single block is not considered a tower, it's just a block. But as soon as you put another block on, it becomes a tower. How many different towers could be made, but they got 3 blocks high? The colours are important because it means the actual order of placing the blocks is important, because we'll get different towers depending on how we arrange the different colours. So 5P3, 5 blocks to choose from, and I'm going to get 3 of them. So 5P3, there are 60 towers we could make. Well, how many in total? How many in total? Okay, well, 2 block towers would be 5P2. That's 20. 3 block towers, well, we just worked that out. That's 60. 4 block towers ends up being 120. 5 block towers is also 120, giving us a grand total of 320 possible towers we could make. Voila! So begins our journey into combinatorics.